Something like this. What if we did? What if we wanted to take a limit, find the end behavior of a function like this? Say we had f of x is the sine of 7 over x minus 3/2 pi or something like that. We're taking the limit as x approaches infinity. Okay, what are we going to do about something like that?
Multiply it by 7x times 3 pi, which is over 7x.
Say that again.
Multiply it by 1, but 1 is a fraction of 7.
Oh, you get a common denominator is what you're saying?
No, like, take what's inside
Mhm.
the sign and then make it a function of 1. So it's 7
Okay.
over x minus 3 pi. Which
All over 1?
No, over itself.
All over itself.
So then you get,
You want to come do it? I'm curious what you're
Multiplying times 1 using that as the.
Oh, I got you. I got you.
and then that, and then you find the limit of that.
Okay. And this is all inside the sign? Okay, but if we did that, that's interesting, an interesting approach. I always like to see what people are thinking about this. So if we did that though, if we cross those out, aren't I right back where I started?
No, but
Yeah, am I
So it's
missing?
not
Doesn't
inside, though.
sign cancel?
Oh, okay, but this is inside the sine function.
yeah.
See what I'm saying? So if I have something like sine of theta, and that's inside the function, I can't do something like that, because this theta's, the sine of theta is no longer an angle, right? When I input an angle into a sine function, I'm getting back a number. So this is the way, and this is something that, you know, you guys haven't worked a ton with trig stuff, but you have to treat that as one thing. It's not two things. It is one thing. That's one number, or it's one function that produces a number. See what I'm saying? Okay. So we can't do something like that. But think about what we talked about yesterday. Question? We will make tables with this stuff. I'm going to hold off on the tables. I'm going to give you an assignment. Kind of the 3-6 assignment is essentially nothing new, but it's just tablifying everything that we've done. So on this stuff right here, the 3-5 assignment, I held off on doing any of that yet. The 3-5 assignment really is just 90% of it is what we did yesterday. Now think what we did yesterday with rational functions, right? And we even went one step further than we needed to with the rational functions. We started talking about slant asymptotes because I wanted you to see that behavior, but we won't really deal with that until the next assignment. But we had 3 cases, right? If we had a rational function where the top polynomial was higher order than the bottom, what could you tell me about the limit? Does it exist? Remember from yesterday, if I go back, if we looked at an example like that, right? And the limit did not have a horizontal asymptote, did it? Right? This one ended up having a slant asymptote, but really we're not going to deal with that until we tablify things, right? I mean, I wanted to show you an example, but we'll come back and review that again, like on Monday or Tuesday, right? What about something like that, where we had polynomials of like orders, top and bottom? What was our simple rule? Nick, you came up with a rule for that. What was it?
Front numbers.
Yeah, you just take a ratio of the leading coefficients, and that's the value of the horizontal asymptote, right? If the bottom is a higher order polynomial, the limit's always 0. And so the horizontal asymptote is just the x-axis, right? Okay. So what's going on with a function like this? Now you got to think about this in 2 parts. Question?
But you can't, for like this, you can't plug in like say 20 for x, and then do like 100 and see what it's.
Well, you could. In fact, what you could even do, we know that in the limit that x approaches infinity, we know what some of the internal behavior of this function is. Inside the argument of the sign, right? So inside, what's inside the sign function, there's something that you can identify what's going on with that term. What's that term approaching as x approaches infinity?
0.
0. Yeah, right. That term approaches 0, and so what's left? Negative 3/2 pi, which is a point we know, right? What's the sign of negative 3/2 pi? What is it again? It is 1, you're right. Yeah, it is 1, right? Because think about the unit circle, right? We're starting here, but we're going in the negative direction to there, right? So it's positive 1. Okay? Make sense? So 1 is the answer. That's it, right? My point is just that this rational limit, it was still useful for us to know how to deal with the rational limit, even though it was inside of another function, right? This is a composition of functions. It doesn't matter. The limit of 7 over x as x approaches infinity, it still acts the same way we talked about yesterday, right? It just so happens, though, that in this case, the output of that rational function became the input of a sine function, right? Okay. Does that make sense? What about something like... What if I wanted an end behavior model? So I'm going to give you a different kind of question here. This sounds really impressive, but it's really simple. You'll get this. So what if we wanted the... And let's say we're going to make it a power function. I'll specify power function model. What's a power function? It's just what it sounds like. It's a function. That's a function that's a power, right? So f of x could equal a times x to some power. That's it. That's a power function, right?
So it's going to be x that is to the power?
Yes, in a power function it is, yeah.
Yep. What would we find in the last question? Like what I know that we found one of them. What is that? Is that not
Limit.
That last question?
Yeah.
So yeah, so that's the limit. So in other words, if we were to graph this thing, all this is telling us is that if we were to graph this function, and I could have put a plus or minus there too, couldn't I, in that case? Either way, that's going to 0, isn't it? Right? So what that's telling me is that the large-scale behavior, it's going to have this horizontal asymptote. And so way out at the tails, it's going to stick to that function. Now, it might oscillate about the function, right? This one will oscillate about the function a little bit. But in here, we don't know. It's going to be bizarre. We'll get to that when we make tables, right? There's going to be, could be vertical. Well, there won't be vertical asymptotes, but there'll be some weird behavior in there, right? But out here at the ends, it's going to be really boring. It's just going to stick to that horizontal asymptote. And that's what this tells us, right? End behavior stuff. Okay, so what's the end behavior model in terms of a power function for something like this? F of x equals, what's the end behavior model for that power function, or for that rational function? Yeah, it is going to be 0, but if I wanted to describe it in terms of a power function, actually, let me make this, you know what, let me do this. Let me make this 4. That's probably 50%. What's it going to be? It would be a slant asymptote. What's the power function going to be? Or what's the function that describes it, the power function going to be? Okay, all I got to do in this
X over
case
4.
is just look at that ratio.
It's going to be x over 4.
It's going to be x over 4. That's it. Okay. What if we did the same thing for g of x? What's the end behavior model going to be for that one?
3x squared over 2.
Right? So what's that mean? Well, if I were to look way out at the tails of this thing, that's the behavior we're going to see, right? But let me demonstrate that. Like if we were to, let's just look on, I think it helps to see this stuff a little bit on Desmos. So okay, so here's that model, right? There's that function. Okay, if we instead just graph, call it h of x, just the end behavior model, you told me it was going to be 3/2 x squared, right? Okay, it doesn't look super close to it at that point, but obviously what are you going to predict is going to happen if I zoom out?
This is just about the same.
Yeah, if I go out far enough, they look the same, right? You see my point? I mean, it's a good descriptor of the function at large values of x, okay? So not a big deal. What about, okay, so that covers those. Not much of an extension. This is the stuff that's going to be, oh, I got one more. What that one? And well, as x goes, what do you mean by that? As x goes to plus or minus infinity. We just have to think about this in terms of the dominant terms on the top and the bottom, right? Remember that graph we did yesterday where it's, you know, if the thing where it looked linear and then it looked, but after a while you saw that the dominant term was just in the polynomial was just the highest power of x, right? Okay, so on the bottom it's an x squared. Good. So on the bottom, the dominant term is x squared. What's the dominant term on the top? Yeah, it's the negative 3x, isn't it? Right? What about these sines and cosines? Well, what if I made this like an x to the 10th? Does that become the dominant term? How come? You're right. How come? Yeah, because it's inside a cosine. What's the maximum output of a cosine function? Yeah, minimum is -1, right? So the sine and the cosine, those are examples of what we call trapped functions, right? They're trapped between finite values, and so they might as well be 0, right? As x goes to infinity, they get left behind, and so really all we have to worry about is just the rational function. This is the same thing, and this is weird, But this is exactly the same thing as the limit of negative 3x over x squared. Are these functions the same? Not even close, right? But in the limit that x is going to plus or minus infinity, they are, right? Because in that limit, only the dominant terms are going to contribute from the top and the bottom, right? So what's the answer?
Negative 3 over x, 3 over x.
That's a negative 3x over x squared.
Negative 3 over x.
What's it going to be?
Negative 3 over x.
0. How come?
Because the bottom's growing fast.
Yeah, bottom's growing faster than the top. So you're right. So when you guys say negative 3 over x, okay, that's true. That's but let me, I think I can see potentially one little misconception popping up
But
here.
as that goes to infinity, it approaches.
Absolutely. See, that's just the end behavior model, right? So yeah, we can say that. We could say that that's the same thing as, now I can't say that it equals negative 3 over x, because it doesn't. What it equals is the limit of negative 3 over x, right? The limit of this function equals the limit of that function. What is the limit of that function? 0, right? See, we're asking for the limit. Now that's different. I want you to see this here. That's different than when I ask for an end behavior model. If I want the end behavior model of this function, well, that's it right there. If I want to have a description like a kind of an envelope, we call that in math. We want an envelope of the function, meaning on large scales, what does it fit to, right? Envelope is like a curvy version of an asymptote, right? So that's what it is, but that's not what we're asking for. When we're asking for the limit of a function, we're wanting back a number, right? Or in this case, well, yeah, 0 is the number, right? We want to know what is the value going to be way out there, right? We're asking for a numerical answer. End behavior, we're asking for a function that describes it, okay? All right, last one. That make sense? Questions? Give me a thumbs up, thumbs down, thumbs sideways on this. Okay. Okay, I mean, we'll keep going with it. So how about this then? What about if I did something like this? The limit of the function negative 3x plus 2 over the square root of x squared plus 9. And we're taking the limit as x approaches, how about infinity? I want to see if you guys can come up with a clever way. There is I mean, we could just do the math here on this one and go through an algebraic process and come up with an answer. But there's a much more elegant way to do this. We could think about this using the concepts we've talked about, and we could bypass a lot of algebra here and come up with a general rule. Now we said for a rational function, the end behavior of the function is determined by just the leading terms, the dominant terms on the top and bottom. The leading term on the top is what? Negative 3x. Okay, that one's, there's the dominant term on the top, right? Okay, on the bottom, it's not a polynomial, and so in a sense, we can't really say, okay, well, it has a leading term, but it's a composition of functions, right? It's a square root of a polynomial, right? And so in the limit that x goes to infinity, the polynomial that sits inside the radical, what's going to dominate the behavior of that function?
X.
The x squared is, right? And so sure, we're going to be taking a square root of an output of the polynomial, but in the limit, the output of the polynomial is clearly dominated by the x squared, right? Okay, well, what's the definition of the square root of x squared?
X.
No.
Plus minus.
Okay, so
Positive X.
close. The square root of x squared, think about the behavior of that. Let's call that a of x, some function a of x. Think about the behavior of that. If x is positive, it's giving you back x, doesn't do anything. But what if x is like -3?
It's gonna be positive output.
Okay.
Absolute value.
It's an absolute value, yeah. This is the definition of an absolute value function, right? Okay. So then, what does that effectively make the square root of the dominant term on the bottom? Absolute value of x, yeah. Yeah, isn't that close to home when x is not approaching infinity? No, it's not. It's much more complicated. But in the limits that x approaches infinity, the bottom effectively becomes the absolute value of x, right? So what we end up with here then is the limit of negative, it's equal to the limit of -3x over the absolute value of x. Okay? Well, let's look at this animal. What is this? X over the absolute value of x. Let's just analyze that function. What do you think that's going to do? If we think about that as a piecewise function, x can't equal 0, right, for that function. Is that a problem for us? Is that a problem for us? No, it's not a problem at all, right? Because in our limit, we're way out at the tails anyway, right? It's going to, okay, so when x is greater than 0, this function is equal to 1, isn't it? Right?
It's less than 0 is equal to -1.
Aha. When x is negative, it equals -1. So it's just a step function, right? And we can see that. If we look at this on Desmos, we can see that behavior. And Desmos makes calculus way better. I should just do that. So if we just do absolute value x over x. Oh, okay. Okay. I'll show you something. Notice, so that's h of x. We'll call this j of x. Turn this one off. Oops. Okay, now notice on Desmos, it doesn't, one thing I wish you could do, it's not showing us the endpoints, right? But is this function defined at 0? Like if I do j of 0, it's undefined, right? There's j of x, there's h of x. They're the same thing, aren't they? Right? Doesn't really matter. The reciprocal of 1 or -1 is itself, right? So then what's going to happen if we want to evaluate this function? Okay, let's put the more complicated function in. Oh, darn it. Let's put the more complicated function that we started with. Come on. Just stay there. There we go. So we had -3x plus 2. Divided by square root. How the heck do I do that? Oh, I gotta go down here. There we go. Square root.
SQRT.
Does it do that too?
I think.
Squared plus 9. Okay, let's look at this function. Let's graph this one next to it. So that's in red. Okay. So ours, on a large scale, they don't look very similar, but they actually shouldn't, should they? Because I kind of put in the wrong function.
Yeah, it'd be -3.
It should be -3x over absolute value of x. What's going to happen if I multiply this blue function
It's just gonna,
by -3? What's that do?
it's gonna make it -3 to the right.
So I can put the -3 out front or on top. If I multiply a function by a constant, what's the 3 going to do? If I multiply a function by 3, what's that do? How does that transform a function?
It changes on the y.
Okay, it's vertical dilation, right? If I multiply x squared by 2, it's just going to take the parabola and stretch it by a factor of 2, right? So the 3 does that. The negative is going to do what?
It's gonna,
If I multiply a function by negative 1, what's that do? Flips it over the x-axis. Good. So there's, right? Okay, now let's turn this one on, and let's look at these. Isn't this cool? I mean, man, Desmos, I really like this. I like this Desmos thing. So you can already kind of see that if I zoom out, it fits the asymptotes, doesn't it? Right? So how do we come up with a quick sketch of that just from our answer? Well, it's pretty simple, right? We know what this step function is, and we're just going to multiply that step function by -3 and do the two transformations you just told me about. We're going to reflect it and stretch it vertically by 3. So this problem looks pretty complicated, but if you just focus on the dominant parts, you can see that this square root of x squared is becoming an absolute value of x, right? And you have a -3x on the top. Okay, so try one of these on your own. Just tell me what you're going to get from something like this. How about if we have... Oh, so, okay, yeah, we never answered it. So what is the limit of this then as x approaches infinity?
-3.
It's going to be -3, right? Because x over absolute value of x, for positive values, that limit is going to be 1, right? See what I'm saying? Times -3 is -1. Because this is the step function that always, the piecewise function that always goes with x divided by the absolute value of x, or its reciprocal. Yes, sir?
So it'll just be the first number.
Yeah, okay. But be careful with that. What about this one? What if I have the limit of square root of 2x squared minus 3x over x plus 4 as x approaches negative infinity? Kind of, but not really. I mean, it's the same concept. Okay, what is effectively the dominant term on the top?
X squared.
Well, okay, but it's
2x.
this whole part right there, right? Right, the square root of 2x squared, which is, what is that? That's the square root of 2 times absolute value of x, right? Divided by x as x approaches negative infinity, right? So we know what that behavior is, right? That's right. So this is going to be, you know that when x is positive, it's 1 when x is positive, and it's -1 when x is negative, right? So in the limit that x approaches negative infinity, what's that value? Exactly. -1, right? So this then becomes, it approaches negative. Did I say negative infinity? Okay, good. That's -1, right? Because that's negative. So this becomes square root of 2 times -1. So it's
Negative square root.
negative radical 2. So you got to be a little bit careful with, right? You got to look at the fact that that's negative.
So if that was positive, it'd be positive.
Yeah.
So it's just whatever infinity approaches plus in front.
Yeah, exactly. Because the step function has values of either 1 or -1.
Yeah.
Right? But I mean, you got to be, the other thing I just wanted to show you is like when you have a square root of 2x squared, sometimes that's, you see where that square root of 2 comes from, right? Because if I take the dominant term inside the radical is 2x squared, and the square root of that would be, because we know the square root of a times b equals the square root of a times the square root of b, we can split that into the square root of 2 times the square root of x squared, right? But yeah, I mean, what you're saying is true. You just have to be you gotta look for which side you're going to, right? Okay, make sense? Try it. We'll do a lot more of this stuff. And we're gonna look at functions like this on a table too, right? Work on the assignment. How much time we got? Tons of time, probably. 8 minutes, yeah. Okay. I'll let you work Monday. How's that? Yes, ma'am.
Okay, I mean, I understand, like, how to get the answer, but I don't understand why it's the same.
Okay.
Like, how do you affect that?
Which one are we looking at
Like,
specifically?
well, all of them really, but I know how to get the answer, but I
Mhm.
don't know how to answer, like, why it equals that on the graph.
Okay.
I don't understand.
Okay, so what you got to think about here is when you're taking a limit of something, remember that like as x approaches infinity, you can never get there, right? But you're specifically saying what's happening to this function way out as we get infinitely large. As we get infinitely large, if I look back, these are your notes from yesterday. If I
Yeah.
go back a page, so if we look at like, were you here the day we did the?
I was gone on Monday.
Oh, on Tuesday, you mean?
Oh, yeah.
Yeah, okay, so this stuff right here, this, like in the textbook, it would be, where would they do that? Right here, this stuff, right? Here's how they would describe it. If the degree of the numerator is less than the limit of the rational function at infinity is 0. If they're the same, it's just a ratio of the leading coefficients. If the degree of the numerator is greater, then there is no limit, right? It's going to go to,
Is this like,
it could be slant or it could be, but it's not going to have a horizontal asymptote, in other words, right?
so what we learned yesterday?
Kind of what we reviewed yesterday, yeah, exactly. So, yeah, that's fine, yeah. So then, when you're taking a limit as x approaches positive infinity or negative infinity, you're going to try to leverage some of this kind of stuff. You know, we know that for functions that might otherwise be complicated, when we're approaching infinity, typically there's going to be a single term that's going to dominate the behavior, right? The rest of them are just going to effectively go to 0. In the example we looked at, I'll keep going back to that example we looked at yesterday with that function that went through all these behavior changes, but at the very end, when we kept going out and out and out, ultimately it just looked like a quartic function, right? All the other stuff that seemed so significant when we were zoomed in on it, when we zoom out, you know, we can't zoom out infinitely far, but we zoomed out pretty far, and we could already see that you couldn't even distinguish the two functions, right? It just looked exactly like an x to the fourth function, right? And so when we're taking a limit of something like this, for example, this is the term on top, if we go out infinitely far, that's going to dominate, right? These other two terms, well, you won't even see them, right? And you might think, well, yeah, but if you're going infinitely far, they get totally extinguished, right? Because you can't get to infinity. That means if you're going without limit, then this one is just going to absolutely dominate these other two to the point where they are indistinguishable, right? On the bottom, same thing. But this is going to be the dominant term. And so even though this whole thing looks pretty complicated, we know that the limit of this complicated function is going to be exactly the same as the limit of that term divided by that term, right? Because look where we are, right? We're way the heck out there. Way the heck out there. All this other complicated behavior is long gone. Did you see kind of the line of thinking we're doing there? Right? And so you're just trying to get an answer. You just want to know, is this thing going to have a horizontal asymptote way out there or not, right? If it does, then in this case it's going to be 0, right? Because that term over that term, we know that the limit of that's a rational function, right? That's a lower degree polynomial than that is. And they're monomials, but those are, they're just polynomials. And so it's going to go to 0. So we're just trying to, we're not even worrying about all the complicated stuff when we're doing end behavior. We're taking infinite limits. We're just asking what's going on. Can we simplify what the behavior is going to be way out there, right? Now, next section, we're going to take a function like this, and we'll say, okay, now we've already done this now, right? We've already said way, like this one has a horizontal asymptote of 0. So way out here, it's going to stick to that. Way out here, it's going to stick to that. What's going on in there? Well, then we got to do first derivative test, maybe second derivative, right? We got to go look for critical numbers and see if we can find where the peaks and valleys are, and that's way more complicated, right? But the end behavior stuff it simplifies, right? Because the function becomes simpler way out there. Does that kind of make sense? I mean, it's I know it's kind of a weird concept, and sometimes I think people rebel against it because it doesn't seem exact. But it is. But that's the thing about limits. They're weird. When you're approaching infinity, that is exact. The limit of that is exactly equal to the limit of that. It is. Not in close, but out far it is. Okay? How about like with this one? Right? Do you see what's going on with that one?
Yeah, the that's still down.
Yeah, quick question. Oh, yeah. You emailed it to me? How come I didn't get it? You sent it to my... Oh, there it is, right there. Whoops. There's nothing attached there.
See, I think I could just get on my Google account on that right there.
Sure. Yeah, let's do that.
It's fine. How's that paper supposed to do?
I'll print you guys a bit.
Print to 310.
How do you cite it?
Oh, so